All right, hello. Today we are going to be talking about Chapter 2, Acids and Bases. So the main idea of acids and bases is there are three different concepts: the Arrhenius concept, the Bronsted-Lowry concept, and the Lewis concept. The two that we are going to be focusing on mostly is the Bronsted-Lowry and the Lewis concept. And specific to acids and bases, we are going to be focusing the most on the Bronsted-Lowry concept. So the Arrhenius concept is essentially when you put an acid or a base in the water, it's going to generate either hydrogen positive ions or OH negative ions. It's one of those two. An acid would generate this in water, a base would generate this in water. Okay? The Bronsted-Lowry concept is a little bit different. The Bronsted-Lowry acid is a proton donor. So the acid would give off a proton, and when going back to the Arrhenius concept, it would give off a hydrogen to water, giving off hydronium hydrogen plus ions. Okay. In addition, the Bronsted-Lowry base would be a proton acceptor. So in the case of the Arrhenius definition, it would be accepting protons from water and create OH negative ions. Okay. And so then that's how that ties back to the Arrhenius concept. But for our purposes, we are going to be talking about more about acids being hydrogen donors and bases being hydrogen acceptors. Okay? Usually we will say hydrogen or proton. The Lewis concept is a little bit different. The Lewis concept has an acid being anything that will accept electrons, and the base being anything that will donate electrons. So for both the Bronsted-Lowry concept and the Lewis concept, the base has to have a lone pair to either accept a hydrogen in the Bronsted-Lowry case, or a pair of electrons to donate to an acid in the Lewis concept. And sometimes you'll see Lewis acids and bases being referred to as nucleophiles and electrophiles, and we will get into that a little bit later. All right. So let's look at a few examples of a Lewis acid base or Bronsted-Lowry acid base reaction. We can see here that HCl is our acid, and it's going to donate a proton to the base. We can see here that the H from the HCl added on to the H2O, the water, and made H3O positive, making hydronium ions. Okay? And we can also consider that the parts of the product that are associated with the acid, so in HCl's case, that'd be Cl negative, we would consider this a conjugate base. And we consider this a conjugate base because you can see here how this chlorine is now more likely to accept a hydrogen than donate one, seeing as it doesn't have any more hydrogens. So in this case, Cl is now the conjugate base of the HCl acid that we started with. On the other hand, we start with water as our base, as our hydrogen acceptor. And we can see on the product side that we end up with H3O, and then the oxygen has an extra hydrogen atom attached to it. So it's more likely to donate a proton now than accept a proton. So now this guy here is going to act as a acid rather than a base. So we call it a conjugate acid. Okay? And so this is terminology that I'll be using throughout this chapter. And so let's go on to, so these are some common Bronsted-Lowry acids and bases. And you can see the main feature of a Bronsted-Lowry acid is that it contains a hydrogen ion, or not a hydrogen ion, a hydrogen atom, also known as the proton in this case. And we can see that Bronsted-Lowry bases all have that lone pair where it can accept the hydrogen from the acid. That's important. All Bronsted-Lowry acids will have an available electron pair somewhere, and all Bronsted-Lowry acids will have an available proton or hydrogen atom somewhere. Okay? So let's continue on. So the general idea of an acid, or the general mechanism of an acid-base reaction, is we can see here that the acid gets rid of its HA bond. So it gets rid of this bond right here. So that bond breaks, and then we can see that an HB bond is created. To do this, we can represent the movement of electrons through arrows. So in this case, we can show that this bond breaks and the electrons from the bond end up on the conjugate base. So you see here that these electrons on the conjugate base were the electrons that made up the hydrogen conjugate base bond. And we can see here that our base, it uses its free lone pair of electrons to make a new bond with the hydrogen atom that just left the conjugate base. And then we end up with our products on this side, where the lone pair from the base is now a part, is what makes up that HB bond, okay? And so this is what we call a mechanism. A mechanism shows the movement of electrons using arrows. A double-headed arrow shows the movement of 2 electrons, and a single-headed arrow shows the movement of only a single electron, which we will get into a little bit more in later chapters. So if we scroll down a little bit and look at this example of an acid and a base, we can see here that the acid breaks its bond, which goes onto the conjugate base, and then the base makes a new bond with the hydrogen right here. Okay, and we can do that with every single acid-base reaction. So if you're asked to draw the mechanism of an acid-base reaction, this is what you would draw. The hydrogen conjugate base, base bond breaking, and the electrons going onto that conjugate base, and the base grabbing the hydrogen from the acid and making a new hydrogen bond, okay? All right, so let's continue on a little bit. So here are some examples. So draw reasonable products for the following acid-base reaction. So what's important here is that it's telling us what is acting as the base and what is acting as the acid. And this shows us an example where the acid can also be a base and the base can also be an acid. It's just important to note that when given these designations, that they're going to act a little bit differently. So remember that the acid is going to lose a proton. So in this case, this bond is going to break, and the base is going to gain a proton. In this case, the nitrogen is going to gain that hydrogen bond, and we end up with the final product of OH with the oxygen having a new lone pair, which I've drawn in red, which is from that former proton bond, and it's going to be overall negatively charged. And this negative charge comes from the formal charge on the oxygen, because if we do the formal charge equation, just as a reminder, the formal charge equation is the number of valence electrons minus the number of bonds, which is number B here, minus the number of electrons in lone pairs. And if we apply that to this oxygen here, we know that oxygen has 6 valence electrons. It has 1 bond here, and it has 6 electrons in lone pairs. So it has an overall formal charge of -1. And so then we designate that right here, okay? So generally when the acid loses a proton, it's going to become more negative. So if we started out with something positively charged, it's going to become neutrally charged. If we start out with something that's neutrally charged, we're going to end up something with that's negatively charged. If we start with something that has a charge of -1, it's going to acquire a charge of -2 after it acts as an acid, okay? And so now we can see that there's our conjugate base, because now it's more likely to accept a proton, and it was our acid in our initial equation. And then we end up with our conjugate acid here. So this is nitrogen. So it gets a new hydrogen bond, which I will draw in red. It has its old hydrogen bond from before, and then it has these other 2 CH3 bonds, which is represented just by those 2 lines. And we can see here that this nitrogen is going to gain a +1 charge. If we look at its formal charge equation, nitrogen starts out with 5 valence electrons. It has 4 bonds here and 0 electrons in lone pairs, so it has a +1 charge. And similar to how a conjugate base is going to become more negative, usually a conjugate acid, which this is in this case, is going to become more positive. So if you start out with something that's neutrally charged, such as in this case, it's generally going to become more positive. It's going to gain a charge of +1. If it starts out as negatively charged, it's going to end up with a neutral charge. If it starts out as positively charged, it's going to become more positive, okay? And so then here's this example where the nitrogen-based molecule is going to act as the base, and the water is going to act as the acid. Now, in this other example here, we can see that the nitrogen-based compound is going to be acting as the acid, so it's going to end up losing its hydrogen, and then the water is acting as a base, so it's going to grab that hydrogen. And so then we end up with, oops, I did not mean to do that, but pause the video if you want to try and do this yourself, but I'm just going to continue on with it. So we can see here that the acid, in this case, nitrogen, oops, I'm sorry, I drew that arrow wrong. It's supposed to go from the hydrogen-nitrogen bond onto the nitrogen. My apologies. And so then we end up with a new lone pair on the nitrogen with its old lone pair from before, and it's two CH3 groups. And again, if we do the formal charge, we're going to end up with a charge of -1. And then if we do the same thing over here with the base, we can see here that that water is going to gain another hydrogen atom right here. And if we do the formal charge, it's going to end up with a charge of +1. And we can see here that this is going to be our conjugate base, and then this is going to be our conjugate acid. Okay, so this is a good example of practicing switching between an acid and a base with the same type of formula. Okay, so let's move on a little bit. So let's talk a little bit about acid strength. Usually in Gen Chem, when we talk about acid strength, we're usually talking about the pKa. And we're sort of thinking about that still here in Orgo, but we generally use a different method of determining acid strength without being given the pKa. So here is how we figure out how strong an acid is when using the equilibrium constant. Essentially, it's telling us how much more product there is, how much more hydronium ions there are over our initial acid and our initial base. And so a larger KEQ indicates that this acid is going to dissociate more into its H plus and A- parts. And so that's what a strong acid is. A strong acid is one that readily dissociates into its proton and its conjugate base. So the more stable the conjugate base is, the more likely the acid is going to become its conjugate base and its proton, and the stronger that acid is. And so we're going to be using that base idea to figure out how strong our acids are. So these slides here that I just went past are discussing predicting acid-base reactions from pKa values. And this is just reiterating that when you have an acid-base reaction, the reaction will always proceed towards the weaker acid and the weaker base pair. Okay? So we will explore that a little bit more, but first I want to talk about how we figure out how strong an acid is without being given the pKa. So we have 4 factors that really affect acid strength: the element effect, the resonance effect, the induction effect, and the hybridization effect. A lot of the time, you'll see people using the acronym ARIO, where A equals atom, R equals resonance, I equals induction, and then O equals orbitals. Okay? So when we're talking about these factors that affect acid strength, we're mostly talking about how stable these factors make the conjugate base. And so the first thing that we look at, the strongest factor, is going to be what atom the proton is directly attached to. So if I had something like CH3 attached to OH, the atomic effects that we would consider here with this proton would only be considering this oxygen. It would not be considering this CH3, because that CH3 is not directly attached to the hydrogen, but the oxygen is. Okay? So let's talk about the atomic effect. This PowerPoint lists the electronegativity first, but I want to talk about the size of the atom before we continue on. So the size of the atom is really important when thinking about the stability of the conjugate base, because the bigger your atom is, the better it's going to hold a negative charge. The example I always like to use is, let's say that our small atom is like a little tiny teacup right here, whereas your big atom is like a big bucket right next to it. And for both of these, we pour some water into it. And the water is representing our electrons and our negative charge that we're adding. In the teacup, it's more likely to spill over and be too much for that teacup to handle, whereas in the bucket, it's going to be a lot easier for it to hold that water or hold that negative charge. So the smaller atom is going to have a harder time holding on to a negative charge than a bigger atom. So the bigger the atom is, the more stable it will be when it gains that electron pair from the proton bond breaking, okay? So you can see here in this example, they're using fluorine versus bromine. And this is part of the reason why HF, or hydrofluoroacid, is really a weak of acid compared to stuff like HCl or HBr. It's because fluorine is so small, it's really bad at holding on to any negative charge, and Br is just much bigger, so it's going to have a much easier time holding on to that negative charge, okay? So you can see here in this example, the relative stabilities of the conjugate bases F minus, Cl minus, Br minus, I minus, it's all dependent on their size, not their electronegativity. And then we can see here that though the stability of those conjugate bases are directly related to the strength of the acid they're associated with, okay? So now we understand that size determines how strong the atomic effects are for an acid. But let's talk about when the sizes are relatively similar. Like if we have a carbon and a nitrogen. That carbon and that nitrogen, or the carbon, nitrogen, oxygen, they're all very close in size. So then we have to look at the electronegativity. Essentially what electronegativity is, it's how well an atom holds onto a negative charge. So it's sort of like the size, but it's not as strong as the size. So we only look at electronegativity when we're in the same row of the periodic table, such as when we're looking at carbon, nitrogen, oxygen, and fluorine, at least in this example. And so we can see here that fluorine is the most electronegative, so it's going to be the best at holding on to that negative charge, and it's going to be the most stable conjugate base and correspond with the strongest acid. Following that is OH. And the reason why we have OH here instead of O negative is because when we're looking at its formal charge, again, to be neutral, an oxygen has to have 2 bonds because it has 6 valence electrons, minus 2 bonds, minus 4 electrons in lone pairs, and we get 0. So to be neutral, that oxygen has to have 2 bonds. And it's the same with nitrogen, the same with carbon, with increasing number of bonds. So here, instead of having O negative 2, they've opted to have OH negative 1, because this is more similar to F negative 1 than O negative 2 would be to F negative 1. So we're considering these guys to be associated with its neutral counterpart, where OH here has 2 bonds, NH2 here has 3 bonds, and C here has 4 bonds, okay? And so back to the atomic effects, we can see that OH has a higher electronegativity than N, which has a higher electronegativity than C, which means that O is going to be more stable than N, which is better than C, and their corresponding acids are stronger for that. And I just want to reiterate that this is the first effect that we look at. So for comparing 2 acids, we first look at the atom that both of them are attached to. So let's say, for example, we have CH3OH versus CH3NH2. So we can see here that our more acidic hydrogens are going to be attached to N and O. And you may be asking why I didn't talk about the carbon-hydrogen bonds. That's because they're much less acidic than the OH bond and the NH bond, and that's because of the electronegativity that we just talked about. And so we can see here that the OH is more electronegative than the N, so this is going to be our stronger acid. However, now I want to ask, what if we have the same type of bond to the atom. So we have two OHs here. This one has this connected to it, and this one just has another CH3 connected to it. How do we know which one is more acidic? So after we look at the atomic effects, now we're going to be looking at the resonance effects. So if both the atoms that the H's are connected to are the same, we're going to look at the resonance. And essentially what the resonance does is it stabilizes the negative charge by distributing it throughout the molecule. So you can see with this example here are our conjugate bases. And remember, the more stable the conjugate base, the stronger the corresponding acid. And so we can see here that this conjugate base on the right has two possible resonance structures. Now recall, when we're talking about resonance structures, the true structure between the two resonance structures is sort of a hybrid of the two. So the electrons are not localized on one oxygen or the other. In this way, the electrons are delocalized and the conjugate base is stabilized. On the other hand, this guy here has no resonance structures, so all of its negative charge is on this one atom right here, which makes that atom more reactive and makes the conjugate base less stable. So the more resonance structures that you have, the stronger your acid is going to be because the more stable your conjugate base is going to be. Okay? So we've looked at the atomic effects. They're the same. If we look at the resonance effects and they have the same number of resonance structures or they don't have any resonance structures, the next thing we're going to look at is induction. And so this is sort of like a worse version of resonance because it also delocalizes the electrons, but it does not do as much of a good job as the resonance structures, because we can see here that the fluorines or the electronegative atoms are going to be pulling that negative charge of the conjugate base. So in this example here, O negative, that negative charge is going to be pulled towards the fluorines that are highly electronegative, because remember, when you're electronegative, you love electrons and you pull them towards yourself. And so in this case, fluorine is very electronegative. It's going to pull those electrons towards itself. However, over here, we can see that this carbon here only has 3 hydrogens attached to it. And we know it has 3 hydrogens attached to it because of, in the line angle structure, there are hydrogens there that are not drawn that make sure that the carbon has its full 4 bonds that it needs. And so we see here that hydrogen is much less electronegative than fluorine. So this guy is going to be more stable because that fluorine helps delocalize the electrons away from that oxygen, and again, make the conjugate base more stable. Okay, so we've gone over atomic effects, we've gone over resonance effects, we've gone over induction effects. If all 3 of those are exactly the same, the last thing we're going to go over is the hybridization, also known as the orbitals. And the rule here is that the more S character you have, the more acidic that proton will be. So when we're talking about S character, we're going to be talking about the hybridization of usually carbons, but it can be anything. So we're looking at sp versus sp2 versus sp3. And so if we're looking at how much S character there is, we can see that in this guy, this first one, sp, we have 1 S over 2 letters total, S and P, which is about 50% S. We can see for sp2, we have 1 S over 3 letters total, so we have about 33% S. And finally, sp3, 1 S over 4 letters, we have 25% S. We can see here that sp has the highest S character, so it's going to correspond with the most acidic proton. So in this case, in this example here, we can see that this carbon here is an sp hybridized carbon. And we know that because it only has 2 electron groups around it. And here on the other side with the red hydrogen, this guy is sp2 hybridized. And again, we know that because it has 3 electron groups around it. Because again, just a reminder, the hydrogens are not fully drawn in, but they will fill in any bonds that the carbon still needs to have its full 4 bonds. Okay? So this carbon's sp2, and then this carbon over here is sp. this hydrogen and this carbon pair is going to be more acidic than this hydrogen carbon pair because this hydrogen and carbon pair has a higher sp character than this one. Okay? And this has to do with how the orbitals are shaped. So you see here that sp is sort of smaller. The electrons are more condensed. They aren't being stretched out over a long area like they are in sp3 or sp2. So sp is overall going to be more stable or more acidic than sp2 and sp3. Okay? And here are like our examples here. So F-fine, which is 2 carbons with a triple bond, has a pKa of 25. And just a reminder, the lower the pKa, the more acidic you are. Ethene, which has sp2 hybridized carbons, is 44 pKa, and ethane with sp3 hybridized carbons has a pKa of 60. Okay? And so then that's the general idea behind acidic, how to tell if something is more acidic or less acidic without being given the pKa values. So let's look at this example here. Which of the following compounds is the strongest acid? So let's recall what we just talked about. ARIO. A, atomic effects, R, resonance, I, induction, O, orbitals, or hybridization. So the first thing we're going to look at is the atomic effects of the atom directly attached to the indicated hydrogen. So we see here in this first one, we see that this one has a nitrogen, the second one has an oxygen, and the third one also has an oxygen. So remember, the first thing we look for is the size. All of these molecules are either the same size or very similar in size. So now we're going to look at the electronegativity. Oxygen is more electronegative than nitrogen. So B and C are going to be more acidic than A. So A is going to be the least acidic, okay? And then now, since oxygen and hydrogen, so the two oxygens are the exact same, so the next thing we have to look for is resonance. So if we take off the hydrogen here, take off the hydrogen for both of them, we have to look for the resonance structures that these can have. So usually when we're looking for resonance structures, we're looking for double bonds that can sort of be traded between carbons. So we can see here that this carbon here is sp2 hybridized. What sp2 hybridized for a carbon means, it means it has a double bond somewhere. It doesn't care where the double bond is as long as it has it. So in this case, an electron pair from this oxygen on the right can move and create a double bond with that carbon, and then the previous double bond can break and go onto the oxygen here. And so then we end up with our resonance structure, where the oxygen on the top now has our negative charge, and our oxygen on the right has that double bond. So we can see here that C has resonance. So C is going to be the strongest acid, followed by B, and finally A is the least strong acid here, or the weakest acid, okay? All right, so let's continue on. So now let's talk about predicting the equilibrium position. Remember in the beginning of this lesson, I talked about how the reaction will always proceed towards the weaker acid and the weaker base. This is because the reaction wants to proceed towards the more stable version of the reaction. So it's going to proceed towards the more stable conjugate base, okay? So what I like to do when given these problems, I like to identify the acids. So in this case, each side has to have an acid and each side has to have a base. Usually our bases are going to be negatively charged and our acids are going to be positively charged, but they can always be neutral. The only condition that for an acid to be an acid is that it has a hydrogen, and the only condition for a base to be a base is that it has an available lone pair that it can attack a hydrogen with. Okay, so let's look at this side. So we see here that the guy on the left has a hydrogen, the guy on the right does not, and the guy on the right is negatively charged. So this one is more likely to be the base, and the one on the left is more likely to be the acid. If we look on the other side of the equation, we can see the exact opposite, which we expect, because remember the acid is going to become its conjugate base. So right here is our conjugate base. And then the base is going to become its conjugate acid, which we see right here. Okay, great. So now what we want to do is we want to compare the stabilities of the base and the conjugate base. Whichever one is more stable is the direction that the reaction is going to proceed towards. So we can see here that they both have the same atomic effect. They both have nitrogens, and they are both going to have resonance. The main difference between these two is that this one has an S, a sulfur, and this one has an oxygen. When we do the resonance effects, I'm going to erase some stuff so I can draw it. When we do the resonance effects, it's going to move that negative charge onto that sulfur or onto that oxygen. So now what we want to do is we want to compare the stabilities of those resonance structures. So let's say that this resonance structure right here, where the nitrogen has the double bond and the sulfur has the single bond and a negative charge, versus the same thing over here, except instead of sulfur, we have oxygen. So we can see here that the sulfur and the oxygen both have the negative charge. So what I'm going to do is I'm going to think back. Which of these is going to be more stable with the negative charge? The bigger one. And in this case, sulfur is bigger. So this guy, the left side of the equation, has the more stable conjugate base. It has the more stable overall. So our reaction is going to proceed towards the left, towards the more stable side of the reaction, okay? And so then that's what you want to do with these types of questions. If it asks you, oh, will this reaction proceed towards the left or towards the right, and it's an acid-base reaction, you're going to look for whichever side has the more stable conjugate base, and then whichever side has the more stable conjugate base, and then the reaction will proceed towards that side, okay? And that's about it for this chapter. We're just naming some common organic acids and organic bases. Generally, organic acids and organic bases are going to be less strong than inorganic acids or bases. Like HCl is stronger than an acetylide ion, which you'll learn about later. Okay? So now let's talk about Lewis acids and Lewis bases. We're coming full circle here. So remember when we talked about Lewis acids and Lewis bases, we weren't concerned about the protons. Instead, we were concerned about the electrons. A Lewis acid is going to donate electrons, and a Lewis acid is going to accept electrons, and a Lewis base is going to donate electrons. So in this case, we can see a common Bronsted-Lowry acid-base reaction, which we talked about a little bit earlier. We can see here that this acid, the same mechanism is going to occur. This bond breaks, and the oxygen is going to make a new OH bond. So it might not be completely clear how we donated an electron pair or how we accept an electron pair, but we can see here that the oxygen became positively charged, the chlorine became negatively charged. Overall, the chlorine gained electrons, and overall, this oxygen lost electrons. Okay? We can also consider these reactants as either electrophilic or nucleophilic. Electrophilic basically means that you love electrons, you want more electrons, and that would be considered the Lewis acid. So right here is our electrophile. Okay? And then a nucleophile loves nucleuses. It wants more nucleuses. It wants more protons, it wants more of all that stuff. So our Lewis base is going to be considered our nucleophile. Okay? And generally, a nucleophile is going to attack a nucleus, and an electrophile is going to gain electrons from a broken bond. Okay? All right, and we can see here a more traditional version. I guess not. So what I want you guys to do is I want you to pause this video or do whatever and tell me which one of these is the electrophile and which one of these is the nucleophile. I'm just going to answer it right away, right now. Okay, so we can see here that this Lewis acid, it gained electrons. It's our electrophile. We can see here that this cyclohexane or cyclohexene gained a hydrogen from that double bond. It's the nucleophile. Oops, sorry, I wrote it on the wrong side. It should be the nucleophile over here. Okay, and this will make a lot more sense when we get into more organic reactions and stuff. It's just important to keep these terms in the back of your mind just so you know what's going on. And I think, so this is talking about more about the Lewis definition. Again, to be a Lewis acid, you have to be able to accept protons. I mean, sorry, not protons, but electrons. So in this case, boron is our Lewis acid because it has an available place for a lone pair, but it's just as happy only having 3 bonds. And our Lewis base is going to be water because it's donating its electrons. And again, Lewis acid, electrophile, Lewis base are nucleophile. And so I think that's about the end of the more important parts of this chapter. Yeah, so let's see. Yeah, so this is just talking about the curved arrows and Lewis acid base reactions. Sometimes there's only one curved arrow because you're making a new bond between the acid and the base and making an acid base complex. But this I have not, in my experience in this class, I have not been asked too much about acid base complexes. I've been more concerned about whether an acid is a nucleophile or electrophile, at least in terms of Lewis acid and Lewis base reactions. All right, so that was chapter 2, acids and bases. Let me know if you have any additional questions and I will be sure to answer those right away. Thank you.